Hello everyone. Today I'm going to talk about equilibrium points. So in the last video we talked about what is the meaning of a state equation, that is x dot is equal to f of t x u, where u is the control input, x is the state, okay, and t is the time. So now equilibrium point means x is equal to x star is said to be equilibrium point of this equation if the state means x of the system starts at x star and it will remain at x star for all future time. What it means is that if I can explain this using this pendulum, okay, so let's say this pendulum is in the vertical position, yeah, in this position. Now if you start this pendulum at this position, the position of the pendulum will remain as it is for all the future time. Yeah. So this state I am calling equilibrium state. Equilibrium state. Equilibrium state of this pendulum. Okay. Now if you talk about this position, if you start your pendulum in this position, then the pendulum will not remain in this position. When you leave this pendulum, the pendulum will keep oscillate like this. It will go like this and it will come like this, and finally it will converge at this position. So this position is the equilibrium position. Okay, so it means that when the pendulum is in this vertical position, then at that point of time the x dot will be zero. X dot will be zero means what? The state of the pendulum will not change. So here we are saying that for an autonomous system, I have defined what is the meaning of autonomous system in the previous video. So please go and watch. X dot is equal to f of x. Now, if you want to find the equilibrium point, what you have to do? You have to put x dot is equal to 0. Yeah. So when you will put x dot is equal to 0, you will get f of x is equal to 0. So the equilibrium point means the roots of this equation. F of x is equal to 0. Understood? Now, the equilibrium point can be isolated or it can be continuum of equilibrium point. So isolated means what? Only one equilibrium point. There is no equilibrium point near about it. Isolated. Isolated means, let's say for example, if I talk about number line, so there is one equilibrium point only, no other equilibrium point. And what is the meaning of continuum? Continuum means there are infinite equilibrium point. One equilibrium point is here, another one is here, another one is here, another one is here, another one is here. So all the equilibrium points are continuum, continuous equilibrium point. Yeah. So these two situations can be there, either isolated or continuum of equilibrium. If I talk about linear systems, for linear systems, we know that the state space equation is defined like this. I am not going to in detail how this equations comes and all, because we have studied about the linear systems in undergrad courses. So I assume that you know what this means. X dot is equal to ATX. AT means A is the matrix function of time. ATX plus BTU, Y is equal to CTX plus DTU. Okay. So this is the linear system and we know so many tools to analyze this linear systems. Okay, so we don't have any problem in that. We can find the transfer function of the system, we can talk about the stability of the system and so on. But now when we talk about non-linear systems, there are mainly two challenges. The first challenge is that superposition principle does not hold. We know that a system is called linear system when it follows the superposition principle. What is the meaning of superposition principle? Superposition principle means additivity and homogeneity. Additivity, additivity and homogeneity. So additivity means what? Additivity means if if it follows this equation, then it is called additivity, and when it follows this equation, it is called homogeneity, where C is some constant. Yeah, when a system follows these two properties, we call that system linear system. But in case of nonlinear system, these two uh, rules or these two laws does not hold with the nonlinear system, so that is a problem. Now the next challenge is, when you talk about nonlinear system, it requires advanced mathematics. So if these two equation follows, then it is easy to analyze the system. But if you talk about nonlinear system, you cannot easily analyze the system. So what can be done with nonlinear system to analyze the system? At least we want to talk something about nonlinear system. So to talk about nonlinear system, the first step is called linearization. Linearization means analyzing nonlinear systems around some nominal operating point. So operating point doesn't mean, but here my concern is equilibrium point. Okay, operating point means equilibrium point. So what we are going to do is that we are going to talk about near about equilibrium point. What is the system behavior near about the equilibrium point? So near about the equilibrium point means that, so I said that for the pendulum case, this position is the equilibrium position, right? So near about equilibrium position means that you need to disturb, if you disturb this pendulum small amount with some small force, if you apply on this pendulum, then what happens is that the pendulum will go here, then pendulum will go here, and then it will keep oscillate, and then finally it will converge at this position. So what we are doing, we are talking about near about the equilibrium point, within some range, how the system is behaving. So we saw that if you disturb the system with some small input, with some small force, the pendulum will oscillate and finally it will converge in this vertical position. So we say that the system, the pendulum, the equilibrium point of this pendulum system is stable. Okay, so this study we call linearization. We will talk about this linearization method in a much detailed manner in the upcoming videos. But here is a problem when you talk about linearization. So what is the problem? The first problem is that it only predict the local behavior of the system. Local behavior means you are only talking about locally what is happening near about the equilibrium point. What will happen if you start very far from the equilibrium point? What is happening with the system? That we don't know. So it only talk about local behavior. Local means near about the equilibrium point. Another limitation is that the dynamics of nonlinear systems are much richer than dynamics of linear systems. So of course, when you talk about the near about equilibrium point means that you are ignoring some dynamics of the system. Yeah, so that is one and another limitation. So basically, from this linearization process, you cannot talk about overall system. You cannot talk about overall behavior of the system. You can only talk about local behavior of the system. Yeah, but at least we can something talk about. At least we can something tell what is happening near about the equilibrium point. So something is better than nothing, right? So linearization is a very important tool, is a very important technique to study the nonlinear system. There are many examples of nonlinear behavior. The first is you can talk about finite escape time. So we know that for a linear system, if your system is unstable, if the linear system is unstable, then we say that the system's state will go to infinite as t tends to infinite, right? But in case of nonlinear system, it can happen that the state will go infinite in some finite time. means some for some finite time system can go to infinite. So this behavior is uh, not visible for the linear system. Second is the multiple isolated equilibrium point. So as I earlier said that for the linear system it will have only one isolated equilibrium point. But in case of non-linear system you can have multiple isolated equilibrium point, and behavior you can study based on the initial state of the system. So we will talk about this in much detail. Third one is the limit cycle. So limit cycle means it is a kind of cycle, it is a kind of oscillation. So for linear system, if you have studied about how to how to talk about the stability for the linear system. So for that, um, what we do is that we try to find the transfer function, and then we try to find the roots of the characteristic equation. So we say that the system will have sustained oscillation if the eigenvalues or the roots of the characteristic equation are at the imaginary axis. So if this is the real axis and this is the imaginary axis, then we say that if the roots are lying at the imaginary axis, then the system will have sustained oscillation. But generally it is not feasible, right? If you disturb the system under some perturbation, because in real life it is not possible to achieve this, right? Because there are always disturbance presence in the real world. So thi- this kind of thing you cannot guarantee in the linear system. So if you destabilize or if you just put some perturbation, then this thing you cannot achieve. So in real life, you can achieve sustained oscillation in case of non-linear systems only. I mean, you have to talk about the oscillation or the sustained oscillations using non-linear systems analysis only. Yeah, so these three mainly. So there are other examples of non-linear phenomena also there, but I have given three examples. Now, whatever we have talked about from the last video and this video, I am going to explain everything with the help of pendulum equation. So let's say this is the vertical axis. Here we have the pendulum bob. This is the rod of length L. So I am assuming that the rod is rigid with zero mass, no mass of this rod. Yeah, and let's say the initial position of this bob is like this. Theta is the angle with vertical position, m is the mass, g is the gravity acceleration. So if we talk about the free body diagram and if you apply the Newton's second law, you can write this equation, right? So you just need to balance the forces. So ml theta dot is equal to minus mg sine theta minus kl theta dot. So this kl theta dot represents the friction force. Friction force means the friction via air. So this basically represents the air friction force due to air. Okay. Now, and K is the friction coefficient. So if you talk about the state space model, then you can represent this system, whole system, using this set of linear differential equation, ordinary differential equation, where x1 is theta, x2 is theta dot. Okay. So this is nothing but x dot is equal to f of x. Yeah. So this is an example for the pendulum case. And if you want to find the equilibrium point, how you have to find? Just put x1 dot and x2 dot is equal to 0. Okay. When you put x1 dot is equal to 0, you will get x2 is equal to 0. Now just put x2 dot is equal to 0 here. You will get this equation. And just solve these two equations. You get this equilibrium. Because x2 is 0, right? This is x2. x2 is 0 already. And when you put x2 is equal to 0, you will get from here sine x1 is equal to 0. So x1 is nothing but n pi. Okay. So what is the equilibrium point? So this is x1, this is x2. So equilibrium points are n pi comma 0, where n is equal to 0 plus minus 1 plus minus 2 and so on. So here you have multiple isolated equilibrium point. So at these x1 and x2, your x1 dot and x2 dot is 0. That's why we are calling it equilibrium point. So as I have said here, that multiple isolated equilibrium point. So you can see here we have multiple isolated equilibrium point. Okay, but please try to note that the non-trivial equilibrium points are these 2 points only, 0, 0 and pi 0. Other equilibrium points are just the repetition of these two equilibrium points. So these two equilibrium points represent vertically down. What vertically down means? This position. Vertically down. Theta is 0. Yeah. And pi 0 represent what? Pi 0 represent vertically up. Vertically up means this case. This is the position you talk about. Vertically up, this is talk about vertically down. And now we know that the vertically down position is the stable one and vertically up position is the unstable one. How can we say that unstable and unstable? If you disturb this equilibrium point with some minute force, yeah, then what will happen is that it will just go down like this. It will never come back here. It will never come back here. If you just disturb this pendulum in this position, the the pendulum will go down and it will stable here. So that's why I'm calling vertically down is the stable and vertically up is the unstable. I hope you understand. Next case, this case is very unrealistic case, but I have given this case because of the better understanding of the system. So if you put k is equal to 0, k is equal to 0 means no air friction is there. That in real life it is not possible. So if you put k is equal to 0, here if you put k is equal to 0, then your state space equation will look like this. Yeah. And now this system is the conservative system. Conservative system means it will keep oscillating. I mean, conservative means the kinetic energy and potential energy. The kinetic energy and potential energy will always be constant. It will keep oscillating. The oscillation will never decay. And other case is that if you are applying a torque, if you are applying an external input, T, then your state space equation will look like this. The only difference is that another force will come here because of this external torque. Okay, so this is our system equation. X dot is equal to f of xu, where u is this control input. So this is all about this particular video where we talked about equilibrium point and the linearization technique. We will study linearization technique in much detail in the upcoming videos, and linearization and linear systems and this pendulum example. Please ask your doubts in comment section. I will try to clear all your doubts about anything whatever I have discussed in this particular video. Thank you for watching.